thank you very much for joining this afternoon and to explain about the company this afternoon. And well, here is Dr. Iwan Hächler. I hope that I pronounce it correctly.
Perfect.
Perfect. Okay.
My Spanish is worse, so don't worry.
Thank you. He's the CEO and co-founder of Solabs Nanotechnology, and a scientist specialized in light matter interaction at the micro and nanoscale. He earned his PhD in mechanical engineering from ETH Zurich, focusing on sunlight-activated functional nanomaterials. I will explain a brief summary of the company's work. Solabs Nanotechnology is an R&D company developing nanotechnologies that make everyday life easier. They offer integrated and fully durable infrared absorbing nanocoatings, and their solutions are designed for application in eyewear, small surface areas, such as car headlights or endoscopic devices, and large surface areas, including car windshield, sunroof, and architectural glasses. Their first market-ready product is the Solar DEFOG technology, SDT, by Solabs, the world's first permanent solution against fog in eyewear, which will be launched in the DACH region in April 2026. The coating absorbs the visible solar energy and retains transparency in the visible over only a few nanometers. And compared to similarly visible transparent photothermal coatings, this represents a measure of 60-fold improvement in terms of absorption efficiency. Solabs improves both fog prevention for fog as well as removal 10-fold compared to uncoated surfaces. In addition, their product extension infrared protection technology demonstrates that thermal stress on the pupil can be reduced by over 50% with a potential health implication for the eyes. So thank you very much. The floor is yours.
Thank you very much. So now I can start.
Yeah, sorry.
Perfect. So hello, everyone. Nice to see you. My name is Iwan. It sounded very complicated, what you've just heard. But my goal is to inspire you that nanotech is cool and that if you have good ideas, you should try and dare a venture because it's an insane learning curve. So that's actually my goal, why I thankfully accepted the offer, and I hope I can give you a little bit of inspiration. And I'm happy to answer all your questions. So really see it as a very informal thing. Can you see my screen?
Yes, we can see you now. It was
perfect.
Just, it was present. Thank you so much.
No worries. Okay, so as introduced, we're Solabs Nanotechnology. We're a spin-off from ETH Zurich, and we believe that nanotechnologies can make life simpler, and we work with advanced infrared absorbing nanocoatings. Now, first of all, just a brief overview of what our company does. The whole research started in 2018 when I was still young and a PhD student. We published our core technology in 2023. And through the publication, we were grateful to receive some media attention, which also inspired me, or we received a market pull because of the media attention from various industries. And that basically inspired me to also dare and make this step into the entrepreneurial world. 2 years ago, we incorporated our company, and last year our patent was granted, and also the whole technology was certified on EYEWEAR, on ophthalmics. So we did all the adhesion, aberration, and so forth tests to really guarantee that it's durable. And in a few months, we will enter the first market, the DACH, the German, Austria, and Switzerland market, with a limited test series of sports glasses, a company that licensed our technology. But let me start first where everything actually started in my PhD. So we focused on the problem of fogging. And fogging is not only for those, I see some of you wear glasses, so you know the problem quite often, but it also occurs in many other surfaces, any transparent surface like a car windshield or a glass, an architectural glass, or sensors in your car. So there are many applications. Now, what is actually the problem with fog, or what is fog? So when we have, for instance, a glass and we have light, these rays can actually just penetrate through and light does not get scattered. But if we have those tiny micro droplets on a surface, the whole light path gets distorted and you can't really see through. Similar when you take a shower and you have a window and you have drops on it, then it can become blurry. Now, one way to prevent this is by changing the surface energy. So you have sprays, or you can make coatings that basically change the surface energy and thereby prevent fog. And now I'd like to go a little bit into the tech, because you like obviously nano engineering. So when you do the physics, you can basically make an energy balance of these surface tensions at each interface. And if you do this energy balance or this force balance, then you can basically determine a so-called contact angle. The contact angle is nothing else but the angle that the droplet forms to the surface. And if a surface really loves water, the droplets spread out very flat and it becomes hydrophilic if it's a contact angle below 90 degrees. Or it can hate water and form a droplet on the surface. And that's exactly the current solution with those sprays or towels, that you change a surface hydrophilic, and through that the light can just penetrate through and light doesn't get scattered. And then if you want to go crazy, you can make a surface super hydrophobic. If you have outdoor clothing, if you like to go to the mountains, then you make it very water repellent. And then you have a very high contact angle. The problem with these is these coatings must be where the water condenses, as you can see, always where the droplet or the water touches the surface. And that means they're constantly exposed to any environmental influence, limiting their durability. So my professor said we need to find another approach, or my research lab, and because we're the lab of thermodynamics, heat is obviously one way. If you have a car, you probably know these heating wires in the rear windshield. So you can actively heat the surface and thereby obviously prevent fog. And this is not very sexy for eyewear, obviously, because you don't want to wear a battery pack. So the question is, how could we use heat to prevent fog or mitigate fog, but without energy supply? And that's where sunlight comes in, because actually half of the solar energy is in the infrared. So it's all energy that our sensors, our eyes cannot see, but it penetrates onto the eye. So there's a lot of energy that's not being used so far, and that's what we wanted to take advantage of. Why? Because thermodynamically speaking, what's very, very interesting is I plotted here a surface at different temperatures and a human breath if you exhale on it. And what you see here is the nucleation rate. So the likelihood that a nucleation, a water drop, can form and grow. And what you see is that a small increase in surface temperature by, for instance, 2 degrees Celsius has a dramatic effect on the nucleation rate by 5 orders of magnitude, for instance. So by increasing the surface temperature only a few degrees Celsius, you can dramatically reduce the likelihood of nuclei to form. The question is, how do we absorb this infrared energy to heat the surface? There are several approaches that exist in research, like plasmonic absorbers, core shell nanoparticles. You can use broadband absorbers. They absorb a broad frequency of wavelengths, or a range of wavelengths, or you can also make multi-layer structures. But all of them have some limitations. And that's actually where we try to find a solution. And again, I'd like to go a little step back to the physics to see how actually physics can be cool and then turn into a venture. Now, let's do some theory first. If you have a nanoparticle and you have an incoming plane wave, so we have light coming in, the energy can be scattered or it can be absorbed. And to compute these amounts of energy, we look at the cross sections. The cross section dictates how much energy is absorbed per incident light. So basically the fraction, or scattered per incident intensity of light. And here the cool thing is, let's say, so basically this cross section dictates if light comes, how big does the particle look to the light? So how much can I absorb? And what's the interesting fact is these cross sections can be bigger than their geometrical cross sections. So if you take these cross section and divide it by PR square, you can find values larger than 1. And that's because the field gets like a funneled into the particle and concentrated. So you can actually absorb more light than the particle has a geometrical cross section. And again, don't worry about the equations. I just want to show you why they are so relevant also in our daily life. If you go a little bit further into these dipole regime, you can see some interesting things in these equations. First of all, you see that the scattering cross section scales with 1 over lambda square, to the 4th. Why does this matter? That means that shorter wavelengths get scattered more. And that's exactly why the sky is blue, because blue light is a shorter wavelength and it gets scattered more when it comes into the atmosphere. So it gets scattered around and we can see it with our eyes. And what we also see in these equations is that a smaller particle, the absorption scales with r cubed, to the power of 3, and r to the power of 6 is the scattered one. So smaller particles absorb light, whereas larger particles scatter light. And the most important thing why I'm showing you these equations is this denominator. Because what you can see, if this denominator is at a certain condition, you have a resonance happening. Meaning, if this term turns into 0, you basically have this term blowing up. So the cross sections blow up. So you have this resonance, and that's called the Froelich condition. And what happens is you have these surface plasmons. So you have like a free electron cloud oscillating on these particle surfaces, and they're confined on the surface. So you basically absorb a lot of energy and you localize it in a very, very thin layer. So that's one particle. But what if we have several particles? Then something interesting happens as well. So you not only have one particle, but you have a neighbor particle. And if you bring them closer together, you can see that there is also some shift in the wavelength and some change in the absorption behavior. So depending on the distance. And what we did, simply speaking, is we took these effects into account and we made a surface that has a very good absorption across infrared wavelengths. And what it does, this is the result. We coated a foil with our coating. This absorbs strongly the infrared and thereby elevates the temperature. And thereby, whenever you exhale on it, it immediately defogs because it's warmer than the ambient temperature and it stays transparent. Okay. And with all this theoretical know-how, we incorporated the company. So now I'm focusing more on the entrepreneurial part. So this is what we did in the lab in our PhD. In all these years of research, a lot of disappointments, but it was always worth it because you have one experiment that works, and then all the 80 experiments before that failed, they're gone because you're happy that the one experiment worked. So my personal experience is stay active and don't give up. Now we incorporated Solabs nanotechnology, and our company basically focuses on 3 segments with 4 different technologies. So we're active in the eyewear sector. We also look into small surfaces like car headlamps or car sensors or endoscopes. Or we also look into large surfaces. But I'd like to talk a little bit more about our first technology, the solar DEFOG technology, which you can see here in action. Again, it's a development, it's our coating. One lens is coated and one not. And you see that both lenses fog up, but the one immediately defogs. It's up to 10 times faster defogging performance than if you have an uncoated lens. Now, how does it work? It's basically, as I mentioned, an ultra-thin coating. It's only a few nanometers, and it selectively absorbs the infrared, up to 70% of the infrared, and it maintains the transparency for those visible wavelengths where our eyes can see, and that's why we can see through. What was important in the development is also how we produced it, because a lot of the micro and nano fabrication is cool, but it's not always easy to scale it and make it repeatable. So we focused on physical vapor deposition, which is the most heavily used or the standard tool used to produce all your sports glasses or all your normal glasses. That means that now transitioning this technology into the market means no extra investments for our customers, so they can produce this on their existing machines. There's no extra labor step. It's applying our technology, our IP, and they're ready to go. And importantly, as I mentioned, the coating can be integrated beneath all the existing standard coatings, which means it's completely protected, completely durable, and you can still apply any other anti-fog solution or anti-fingerprint solution on the surface, so it's not competing with any other technology. The coating also works when it's not perfectly sunny, so it also works on cloudy days, but it's like a solar cell. The more sun you have, the better it is. And this is also important for us now competitively. How do we position our technology against other products? And we say we are really durable. So you buy your sunglasses and you have it for the rest of your lifetime. And it's also multifunctional. So you can combine it with any other technology. So it's not either or, you can still have both. Where is our technology now? We measured all those key performance indices. So we can defog up to 10 times faster. So the defogging time is up to 10 times less, depending on the humidity and the solar intensity. We also prevent fog in some conditions. So some conditions, fog does not even occur. And we also quantified, we are publishing now a paper, which is under review, where we basically assessed the effect on the eye temperature by applying infrared absorbing coatings, where we show that you can reduce especially the stress on the pupil in your eye. And we also produced a material or the coating with various materials. So we have a whole booklet of materials that we can employ and integrate. Now, the current status is we're certified and durable. We're ready for the market launch, which will be in April. And we have proved the production on existing production lines on several different tools. When I say we, this is also a big learning. If you want to go, if you're going to go fast, go alone. If you want to go far, go together. It's always the team. And to be very honest with you, that's one of the most exciting things during this intense period with this startup. It's the team. I never learned so much in my life as in those 2 years, more than in my PhD. There's so many variables affecting us, so many things I was anxious and I haven't known before, and I had to learn in a short amount of time with a lot of pressure. But the team, I'm really proud of our team. I'm supported by Fabrice, a former student of mine, who has also micro nano fab experience. He's also a mechanical engineer. And then Florian, he has a business background, and he's our CFO. And we also have senior level expertise from Patrick. He has lots of experience in sales and marketing and worked for big sports brands. And also, for instance, his last position was at On Running, the shoes, where he helped scaling the company And we can benefit now from all these real world experience that he has gathered and also his seniority. And we also are very grateful for our advisory. So we have advisory from the industry, we have advisory, legal IP advisory, research advisory, as well as business advisory. And what I'm trying to tell you is it's absolutely amazing to see how little I actually know and how much I can learn from these people from different fields and the openness and willingness to learn. And with this, I'd like to close my technical presentation. I want to say muchas gracias. And I'm very happy to take your questions. By the way, there was also a very nice BBC news video about our coating. It's on top of Europe, one of the highest cable car train stations in Europe, or the highest in Jungfrau-Joch. So you have a QR code, you can scan it, and then you also see nice pictures of Switzerland, if you like Alps. Muchas gracias, and I'm happy to take your questions.
Thank you very much, Iwan. It was very nice presentation. So now, do you have any questions, any curiosity, any ask for their experience for him?
I have a question. Which is the material of the nanoparticles that you use for the coating?
Yes, so you're asking about the specific material or how it works, basically, how we plate, or both?
No, the material is the...
So for the coating that we published, we used gold nanoparticles because of their absorption behavior. We also fabricated the coating with other metals that are not disclosed yet, or we also use dielectrics. So it's basically, I always say it's like a hamburger. So you have your buns, and then you have your patty, your meat in the middle. And our IP covers not specifically, let's say, a hamburger. So we can change the beef in the middle. We can make a chicken burger, we can make a vegan burger, we can make a veggie burger, and we can also change the buns. So we can make brioche, we can even make a double, like a Big Mac, basically. It's all protected by our IP. And the core material we used for the publication is gold, but we have other patties, and we also have various buns. In the publication, we showed it's titanium, so titanium dioxide.
And how do you fabricate those nanoparticles using PVD techniques? For me.
Yes. So have you, I don't know, maybe you can help me. Have you been in a clean room, or do you know how a clean room works?
Yes.
Yes.
Perfect. So basically, it's there are different processes in PVD, physical vapor deposition. You can use sputtering, where you basically apply a very strong electric field in a high vacuum chamber. And through the electric field, you create a plasma, and then your ions come out of your material target. And then you have your samples on the top, and through the electric field, they gather on the surface. So that's like sputtering, the technology used for all the architectural glass, basically. Another PVD process, which we focus on now as well, so we can also sputter it, but it's also produced with E-beam evaporation. So you take an electron beam gun and you shoot onto a metal or a dielectric so that it becomes in a crucible, so it becomes liquid. And it's similar when you cook spaghettis. You have the water boiling, and then you have your lid. And on the lid, the water condenses, and it's the same. So you evaporate your material, and it evaporates in the vacuum, and it settles on the substrate.
Yes,
and through
but how do you manage to fabricate nanoparticles instead of thin films? Because as far as I understood, you use plasmonic principle using nanoparticles in the publication code, but with DVD, I usually saw fabrication of thin films. And do you fabricate them in particles?
Yes, it's always a question of the time. It's the same with the spaghetti cooking. Initially, you only have a small small droplets, but then you form a continuous film. And it's the same when you evaporate. So if you evaporate short enough, you only form tiny nanoparticles on the surface. So it's like not a continuous film, but it's still particles.
Okay.
Yeah. And then it's important. So the coating, I showed you the plasmonic absorption, but there are various absorption mechanisms playing into the overall absorption profile, so the absorption spectra of the coating. Yeah, but that's exactly what we play around with the exact thickness and the absorption behavior.
And what about the morphology of the nanoparticles? Which is the morphology you usually use? Like spheres or ellipses?
What is the shape of the
Okay, sorry. So we actually don't have single particles. We have a semi-continuous film. So it looks like a brain structure. So it's not a continuous film nor particles. It's something in between, basically. But usually, a very good question. We have done some research, or some colleagues in my lab, and when they deposit it, it's very hard to obviously control the concrete shape. So what you have is a range of particle size, particle shapes as well, and that actually leads to a broadband behavior because you absorb, because the shape as well, the size, as you mentioned, affect the absorption behavior. So usually when you do that, you have a very broadband absorption at different wavelengths, if that makes sense.
Okay, thank you very much. Very interesting.
Is there any more question? No.
What will be the cost of the glasses in general?
Very good point. I cannot disclose it. So we have, there are two costs. There are always two. No, there's a cost and there's a price. So one is the manufacturing cost, which I cannot disclose, and then one is the price, which I cannot disclose. But what's going to happen is when we sell, we sell it with a Swiss manufacturer. They do sports glasses. They have glasses that with an LCD and a photodiode. So when light hits the photodiode, it immediately tints the LCD. So if you love cycling and you cycle in a tunnel, it becomes brighter, and when you go outside, it becomes dark again. And they have a sales price, and additionally to their sales price, we have a few euros, some euros extra that they can use our coating. But you will see it pretty soon. Yes, then you can look it up online, and then you know the answer.
Okay, thank you.
Sorry for not being able to answer.
Yeah, we understand. Don't worry. I have a question. Yeah, because for PVD normally the coatings are on planar substrate. How can you deposit on curve, like in the EYEWEAR?
Yes, good question. So initially the whole research also started with just plain substrate. But actually the ophthalmic industry, I mean, you always have curved lenses as well when you buy glasses because you need a certain dioptry. So what you do is you basically you have like a how do you call it? It's like a circle on top but has a specific shape. So it's not a flat surface, but you have it like a dome. And then based on the dome, you obviously have a different distance. And through that, you can create uniformity. But it's a very good question because, for instance, sports glasses, they're produced differently. There you usually don't have a dome in the top, but it's like a what do you call it? When you wash your clothes, when you do laundry, it's like a laundry machine, like a huge laundry machine, but you have like plastic shields around it and they circle around. So it's like a big drum. And there, the bigger you get, obviously, the more challenging it gets with uniformity.
Okay,
Yeah.
very interesting. Yeah, because here we can deposit, we have some PVD systems that we normally just do planar. So
Yes,
we don't go further.
we had the same. So also an anecdote. We produce it with PVD and E-beam, and ETH has a collaboration with IBM Research here in Zurich. And because it's the most heavily used tool, I always tell, because actually the whole coding was developed on weekends, because on Saturday nights, the machine was always free. So that's when I went to the clean room, because I had my time to try out things. And there we could only fabricate samples with a height up to 8 millimeters. So very small samples, maybe a few inch wafers. And that was also interesting to scale it to commercial machines, because you all of a sudden have other things like what you mentioned, the curvature and whatnot to think about.
Okay, thank you very much. Is there any more question to Ivan? Yeah, there is one more.
Are you able to make completely transparent glasses with the coating? Or is there any coloring of the glass?
Yes, good question. We have a certain absorption in the visible light for now. We're not completely transparent. We have samples up to 80 to 85% visible transparency. As a comparison, if you have insulated glass, that's also about, depends on if you have 2 pane, if you have 2 windows or 3, you'll have something between 70 to 90 or 80% as well. So we have a slight tint. We can control the absorption profile. So if you only absorb certain wavelengths or if you have a broad behavior, and we're also working on the transparency to further improve it and make it even more transparent.
Is there any more question? No? Well, then thank you, Ivan, again. Sorry. Yeah. Thank you very much, and thank you very much for the advices that also you give them. I'm sure that they appreciate it, because it really is a case that a success case. So finally, his application of his research in the laboratory was applied in the real world. So thank you again, Ivan.
Thank you. And
thank you.
I'd like to mention, if you ever have questions or ventures or anything, I'm very happy to help you and answer questions, because I think it's important to promote it, and don't be scared. Really try and do it. So if you have any questions, if there's anything I can help, let us know.
Thank you very much, Ivan.
Perfect.
Thank you.
Bye-bye.
Bye-bye. One
Adios.
moment, I will stop. One moment, Ivan.
Yes.